sklearn SVM. Description: explain in detail. Support vector machines. SVMs are powerful supervised learning algorithms used for both classification and regression tasks. They are known for their ability to find optimal hyperplanes that separate different classes or predict continuous values. The core principle is to find a decision boundary hyperplane that maximizes the margin between data points of different classes. Inputs. Input 1. Explain in detail training data X, a two-dimensional array or pandas data frame containing the features or independent variables used for training the SVM model. Each row represents a data point, and each column represents a feature. Input 2. Explain in detail target labels Y, a one-dimensional array or pandas series containing target values labels corresponding to each data point in the training data. For classification, these labels represent class categories, while for regression, they represent continuous values. Outputs. Output 1. Explain in detail fitted SVM model, the trained SVM model object that contains the learned hyperplane and other parameters. This model can be used for making predictions on new data points. Output 2. Explain in detail predictions, the predicted output class labels or regression values for new data points, obtained by applying the fitted SVM model to unseen data. Steps. Step 1. Explain in detail data preprocessing. The input data is preprocessed to ensure it is suitable for the SVM algorithm. This typically involves scaling or standardizing features, handling missing values, and converting categorical variables to numerical representations. Step 2. Explain in detail model training. The SVM algorithm is trained on the preprocessed training data. During training, the algorithm searches for an optimal hyperplane that separates the different classes for classification or predicts the target values for regression. Metrics. Metric 1. Explain in detail accuracy for classification. Accuracy measures the proportion of correctly classified data points. Metric 2. Explain in detail precision measures the proportion of correctly predicted positive cases out of all predicted positive cases. Metric 3. Explain in detail recall measures the proportion of correctly predicted positive cases out of all actual positive cases. Metric 4. Explain in detail F1 score, the harmonic mean of precision and recall, providing a balanced measure of model performance. Metric 5. Explain in detail mean squared error MSE for regression. Measures the average squared difference between predicted values and actual values. Visualization plots. Visualization plot 1. Explain in detail decision boundary plot. This plot shows the hyperplane learned by the SVM model, separating the different classes in the feature space. Visualization plot 2. Explain in detail feature importance plot. This plot visualizes the importance of different features in the SVM model, highlighting the features that contribute most to the decision boundary. Fine-tune parameters. Parameter 1. Explain in detail kernel specifies the type of kernel function used to map data points into a higher dimensional space. Common kernels include linear, polynomial, radial basis function RBF, and sigmoid. Parameter 2. Explain in detail regularization. Parameter C controls the trade-off between maximizing the margin and minimizing classification errors. A higher value of C encourages a smaller margin and fewer misclassifications, while a lower value of C allows for a larger margin and potentially more misclassifications. Parameter 3. Explain in detail gamma, a parameter specific to the RBF kernel, controlling the influence of individual data points. A higher value of gamma results in a more localized influence, while a lower value leads to a wider influence. Uncertainty methods. Uncertainty method 1. Explain in detail confidence scores for classification. The SVM model can provide confidence scores for each predicted class label, indicating the model's certainty about the prediction. Challenges and fixes. Challenge 1. Explain in detail overfitting. SVM models can overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in Challenge 1. A small training dataset with a high degree of complexity, where the SVM model learns the training data too well and fails to generalize to new data. Fixes to Challenge 1. Regularization. C parameter reducing the value of the regularization. Parameter C can help prevent overfitting by allowing the SVM model to make some errors during training, thus promoting generalization. Cross-validation. Using cross-validation techniques to evaluate the model performance on unseen data can help detect and address overfitting. Challenge 2. Explain in detail computational complexity. SVM training can be computationally expensive, especially for large datasets or high-dimensional data. Sample use case that resulted in Challenge 2. Training an SVM model on a dataset with millions of data points and hundreds of features can take a significant amount of time and computational resources. Fixes to Challenge 2. Kernel approximation techniques. Approximating the kernel function can reduce the computational cost. Stochastic gradient descent (SGD). Using SGD-based optimization algorithms can be more efficient for training large datasets. Feature selection. Reducing the number of features in the data can significantly reduce the training time. Challenge 3. Explain in detail data scaling. The performance of SVM models can be sensitive to the scaling of features. Sample use case that resulted in Challenge 3. Features with widely different scales can lead to the SVM model prioritizing features with larger scales, potentially affecting the decision boundary and model performance. Fixes to Challenge 3. Feature scaling. Scaling features to a common range, such as 0 to 1, can improve the performance and prevent the SVM model from being biased towards features with larger scales. sklearn SVM Linear SVC. Description. Linear SVC is a linear support vector machine classifier in scikit-learn. It implements a 1vs REST multi-class strategy, meaning it trains a separate linear model for each class, comparing it to all other classes. Linear SVC is efficient for large datasets and performs well when the data is linearly separable. Inputs. X. A 2D array containing the training features. Each row represents a data point, and each column represents a feature. Y. A 1D array containing the target labels for each data point in X. Outputs. Self. The fitted linear SVC model, which can be used to predict labels for new data points. Core. A 2D array containing the coefficients of the decision function. Each row corresponds to a class, and each column corresponds to a feature. Intercept. A 1D array containing the intercept of the decision function for each class. Steps. The linear SVC algorithm learns a hyperplane in the feature space that maximizes the margin between the different classes. This hyperplane is defined by a set of coefficients and an intercept, which are learned during training. The model uses the learned hyperplane to classify new data points by determining which side of the hyperplane they fall on. Metrics. Accuracy. The percentage of correctly classified data points. Precision. The proportion of correctly predicted positive instances out of all instances predicted as positive. Recall. The proportion of correctly predicted positive instances out of all actual positive instances. F1 score a harmonic mean of precision and recall, providing a balance between the two. Visualization plots. Decision boundary plot, a plot showing the hyperplane learned by the model, along with the data points and their classifications. Feature importance plot, a plot showing the coefficients of the decision function, indicating the relative importance of each feature in the classification process. Fine-tune parameters. See the regularization parameter, controlling the trade-off between maximizing the margin and minimizing the training error. A higher C value leads to a smaller margin but lower training error. Penalty. The type of penalty used for regularization, either L1 or L2. L1 penalty encourages sparsity in the coefficients, while L2 penalty encourages smaller coefficients. Loss. The loss function used for optimization, either squared hinge or hinge. Squared hinge loss is more sensitive to outliers, while hinge loss is more robust. Dual. Whether to use the dual formulation of the optimization problem. Dual formulation is more efficient for large datasets with many features, while primal formulation is more efficient for small datasets with few features. Toll. The tolerance for stopping the optimization algorithm. Uncertainty methods. Confidence scores. The decision function output provides confidence scores for each class. Higher scores indicate higher confidence in the predicted class. Challenges and fixes. Challenge 1. Overfitting. The model may overfit to the training data, resulting in poor generalization performance on unseen data. Sample use case. When the training data is very small or contains a lot of noise, the model may learn to fit the noise rather than the underlying patterns, leading to overfitting. Fixes to challenge 1. Use regularization C parameter to penalize complex models and encourage simpler models that generalize better. Use cross-validation techniques to evaluate the model performance on unseen data and adjust the regularization parameter accordingly. Consider using data augmentation techniques to increase the size and diversity of the training data, reducing the risk of overfitting. Challenge 2. Data scalability. For very large datasets, the training time can be significant. Sample use case. When the number of features is very large or the dataset is very large, training can become computationally expensive. Fixes to challenge 2. Use techniques like stochastic gradient descent (SGD) to optimize the model more efficiently, especially for large datasets. Consider using feature selection techniques to reduce the number of features, which can speed up training and improve model performance. Explore using a different, potentially more efficient, machine learning algorithm for large datasets, such as a decision tree or random forest. Challenge 3. Nonlinear data. Linear SVC is designed for linearly separable data, so it may not perform well on datasets with complex, nonlinear relationships between features and target labels. Sample use case. If the data has a nonlinear decision boundary, the linear model may fail to separate the classes accurately. Fixes to challenge 3. Use a nonlinear kernel function within the support vector machine framework (SVC) to transform the data into a higher dimensional space where it may be linearly separable. Consider using other nonlinear machine learning algorithms, such as decision trees or neural networks, which are better suited for handling nonlinear relationships. sklearn SVM. Linear SVR. Description. Explain in detail. Linear SVR is a linear support vector regression SVR model implemented in scikit-learn. It finds a hyperplane in the feature space that best separates the data points while minimizing the Error of prediction. Inputs. Input 1 explain in detail X. This is the input feature matrix. It's a two-dimensional array where each row represents a data point and each column represents a feature. The data should be numerical and appropriately scaled. Input 2 explain in detail why this is the target variable. It's a one-dimensional array representing the values to be predicted. Outputs. Output 1 explain in detail model. This is the trained linear SVR model. You can use this model to make predictions on new data. Output 2 explain in detail predictions. This is the predicted output for the input data. The output is a one-dimensional array of predicted values. Steps. Step 1 explain in detail data preparation. Prepare your input features X and target variable Y. Make sure the features are numerical and properly scaled for optimal model performance. Step 2 explain in detail model initialization. Create a linear SVR object. You can set parameters like C for regularization strength, epsilon for the tolerance of the error, and loss to specify the loss function used. Step 3 explain in detail model training. Fit the linear SVR model to the training data X, Y using the fit method. Step 4 explain in detail prediction. Use the trained model to make predictions on new data by calling the predict method. Metrics. Metric 1 explain in detail mean squared error MSE. This metric measures the average squared difference between the predicted and actual values. Metric 2 explain in detail root mean squared error RMSE. This metric is the square root of the MSE and represents the average error in the same units as the target variable. Metric 3 explain in detail R squared R2. This metric represents the proportion of variance in the target variable that is explained by the model. A higher R2 indicates a better fit. Metric 4 explain in detail mean absolute error MA. This metric measures the average absolute difference between the predicted and actual values. Visualization plots. Visualization plot 1 explain in detail residual plot. This plot shows the difference between the predicted and actual values. It can help identify patterns in the error and check for heteroscedasticity. Visualization plot 2 explain in detail feature importance plot. This plot shows the importance of each feature in the model. Features with higher importance have a stronger influence on the predictions. Fine-tune parameters. Parameter 1 explain in detail C regularization strength. A smaller value of C corresponds to a stronger regularization and a more simple model, which can prevent overfitting. A larger value of C allows for more complex models, which can overfit the training data if not carefully chosen. Parameter 2 explain in detail epsilon. This parameter controls the width of the margin around the hyperplane. It determines the tolerance for errors in the training data. A larger value of epsilon allows for more errors, while a smaller value enforces stricter adherence to the training data. Parameter 3 explain in detail loss specifies the loss function used in the model. The default is epsilon insensitive, which is appropriate for standard SVR tasks. You can also choose squared epsilon insensitive for a more robust loss function. Uncertainty methods. Uncertainty method 1 explain in detail confidence intervals by calculating confidence intervals around the predictions. You can assess the uncertainty associated with each prediction. This can help you understand the reliability of the model. Uncertainty method 2 explain in detail Bayesian linear regression. This approach can be used to incorporate prior beliefs about the parameters and obtain a posterior distribution over the predictions. This allows for a more comprehensive assessment of uncertainty. Challenges and fixes. Challenge 1 explain in detail overfitting when a model learns the training data too well. It may perform poorly on unseen data. This happens when the model becomes too complex and picks up on noise in the training data. Sample use case that resulted in challenge 1. You train a linear SVR model with a very large value of C and a small dataset. The model fits the training data perfectly but fails to generalize to new data points. Fixes to challenge 1. Reduce model complexity. Use a smaller value of C to increase regularization. Increase training data. A larger dataset can help the model learn more general patterns. Feature selection. Remove irrelevant features that might be causing overfitting. Cross-validation. Use techniques like cross-validation to evaluate the model's performance on unseen data and identify potential overfitting. Challenge 2. Explain in detail high-dimensional data when the number of features is very high. Linear SVR may struggle to find an effective hyperplane. This can lead to poor performance and difficulty in interpreting the model. Sample use case that resulted in challenge 2. You have a data set with hundreds of features and train a linear SVR model. The model has poor performance and it is difficult to determine which features are most important. Fixes to challenge 2. Feature selection. Use feature selection techniques to reduce the number of features to a smaller set that is more relevant to the prediction task. Dimensionality reduction. Apply dimensionality reduction techniques like principal component analysis (PCA) to reduce the number of features while preserving the important information. Regularization. Use a higher value of C to encourage the model to focus on the most important features. Challenge 3. Explain in detail nonlinear data. Linear SVR assumes a linear relationship between features and the target variable. If the data is nonlinear, the model may not be able to capture the relationship accurately. Sample use case that resulted in challenge 3. You have data with a nonlinear relationship between features and the target variable. You train a linear SVR model, but it fails to capture the relationship and performs poorly. Fixes to challenge 3. Feature engineering. Create new features that capture nonlinear relationships in the data. Nonlinear models use nonlinear regression models such as support vector machines with a nonlinear kernel or decision trees. Challenge 4. Explain in detail outliers. Outliers can significantly affect the performance of linear SVR, especially if they are far from the hyperplane. Sample use case that resulted in challenge 4. You have a dataset with a few outliers that are very far from the other data points. You train the linear SVR model and it is heavily influenced by these outliers. Fixes to challenge 4. Outlier detection. Identify and remove outliers using appropriate methods. Robust regression. Use robust regression techniques that are less sensitive to outliers. Challenge 5. Explain in detail scaled data. Linear SVR is sensitive to the scale of the features. Features with larger ranges can dominate the model, leading to biased results. Sample use case that resulted in challenge 5. You have a dataset with features that have vastly different scales. You train the linear SVR model without scaling the features and the model performs poorly. Fixes to challenge 5. Feature scaling. Scale the features using techniques like standardization or normalization to bring them to a common scale. L1 L2 regularization. Use L1 L2 regularization to penalize large feature weights, which can help mitigate the impact of features with large ranges. sklearn SVM NUS VC. Description. NUS VC is a support vector classification SVC model that uses a parameter nu to control the number of support vectors and the upper bound on the fraction of training errors. It is similar to SVC, but it provides more control over the number of support vectors and the trade-off between model complexity and training error. Inputs: X training data, represented as a 2D array of shape n samples. N features, where n samples is the number of samples and n features is the number of features. Y target values, represented as a 1D array of shape n samples, where each element corresponds to the class label for the corresponding sample in X. Outputs: Self: the trained NUS-VC model. Decision function X returns the decision function values for the given data X. Predict X returns the predicted class labels for the given data X. Steps: The NUS-VC model constructs a hyperplane that separates the data points into different classes. The new parameter controls the number of support vectors and the upper bound on the fraction of training errors. The model finds the optimal hyperplane by maximizing the margin between the classes while minimizing the number of support vectors. Metrics: Accuracy: the proportion of correctly classified samples. Precision: the proportion of correctly classified positive samples among all predicted positive samples. Recall: the proportion of correctly classified positive samples among all actual positive samples. F1 score: the harmonic mean of precision and recall. Visualization plots. Decision boundary plot visualizes the decision boundary of the trained NUS-VC model, showing the separation between different classes. Scatter plot with support vectors visualizes the data points and highlights the support vectors used by the model. Fine-tune parameters. New: the parameter that controls the number of support vectors and the upper bound on the fraction of training errors. A lower value of nu will result in fewer support vectors and a tighter decision boundary, while a higher value will result in more support vectors and a looser decision boundary. Kernel: the type of kernel function used to map the data into a higher dimensional space. Common kernel types include linear, poly, RBF, and sigmoid. The choice of kernel depends on the characteristics of the data and the desired model complexity. Degree: the degree of the polynomial kernel function. Gamma: the kernel coefficient for RBF, poly, and sigmoid kernels. Coa 0: the independent term in the kernel function. Uncertainty methods. Confidence scores: the decision function values can be used to estimate the confidence of A. Predictions. Higher absolute values of the decision function indicate higher confidence in the prediction. Out-of-bag error for models trained with bootstrap aggregating bagging. The out-of-bag error can be used to estimate the uncertainty of the predictions. Challenges and fixes. Challenge 1: overfitting. If the model is too complex, it may overfit the training data, leading to poor performance on unseen data. Sample use case that resulted in challenge 1: a NUS-VC model with a high degree polynomial kernel and a low nu value may overfit the training data. Fixes to challenge 1: reduce the complexity of the model by using a simpler kernel function or a higher value of nu. Use regularization techniques, such as L1 or L2 regularization, to prevent overfitting. Challenge 2: high dimensionality. If the data has a high number of features, it may be difficult to find a suitable separating hyperplane. Sample use case that resulted in challenge 2: a NUS-VC model trained on a dataset with thousands of features may struggle to find a good decision boundary. Fixes to challenge 2: use feature selection or dimensionality reduction techniques to reduce the number of features. Consider using a different type of classifier that is better suited for high-dimensional data, such as a random forest or a gradient boosting machine. sklearn SVM NUS VR Description: New Support Vector Regression NUS-VR is a type of support vector machine SVM specifically designed for regression problems. It's a powerful algorithm used for predicting continuous target variables. NUS-VR works by finding a hyperplane or a set of hyperplanes in higher dimensions that best separates the data points while minimizing the error. It controls the number of support vectors data points that influence the decision boundary through the new parameter, which directly influences the model's complexity and ability to generalize to unseen data. Inputs: X feature matrix, a 2D array of shape and samples, N features representing the input features for each data point. Each row corresponds to a sample, and each column represents a feature. Y target variable, a 1D array of shape and samples, representing the continuous values that need to be predicted. Outputs: Model: the fitted NUS-VR model object. This object can be used to make predictions on new data. Predictions: an array of predicted target values for the provided input data. Steps: Data preparation: the data is first prepared, which involves scaling features and handling missing values if necessary. Model training: the NUS-VR model is trained on the prepared data using the fit method. Prediction: once the model is trained, it can be used to make predictions on new data using the predict method. Metrics: Mean absolute error measures the average absolute difference between predicted and actual values. Root mean squared error RMSE measures the average squared difference between predicted and actual values, giving more weight to larger errors. R squared measures how well the model explains the variance in the target variable. A value closer to 1 indicates a better fit. Visualization plots: Scatter plot of predicted vs. actual values helps visualize the model's performance and identify potential areas of overfitting or underfitting. Residual plot plots the difference between predicted and actual values to check for patterns or trends, which can indicate model biases. Fine-tune parameters: The new parameter controls the number of support vectors and influences the model's complexity. A smaller value allows for more complex models but can lead to overfitting. See the regularization parameter. It controls the trade-off between minimizing the training error and finding a more generalizable model. A larger value emphasizes minimizing the training error, while a smaller value encourages a simpler model. Kernel specifies the kernel function used to transform the data into a higher dimensional space. Common options include linear, RBF, poly, and sigmoid. Uncertainty methods. Confidence intervals can be estimated based on the model's predictions to provide a range of possible values for the target variable. Bayesian inference can be used to incorporate prior knowledge and provide more robust uncertainty estimates. Challenges and fixes. Challenge 1: overfitting when the model performs very well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: using a complex kernel or a large new value without sufficient data. Fixes to challenge 1: use a simpler kernel, reduce the new value, and/or consider using regularization techniques like L1 or L2 penalties. Challenge 2: underfitting when the model fails to capture the underlying patterns in the data and performs poorly on both training and test data. Sample use case that resulted in challenge 2: using a simple kernel or a small new value for data that requires a more complex model. Fixes to challenge 2: try a more complex kernel, increase the new value, and/or consider using more features or transforming existing features to enhance model complexity. sklearn SVM1 class SVM. Description: 1 class SVM is an unsupervised machine learning algorithm used for anomaly detection. It learns a boundary around the normal data points and classifies any data points outside this boundary as anomalies. Inputs: X a 2D array containing the training data. Each row represents a data point. Kernel: the kernel function used for the SVM. Common options include RBF, linear, poly, and sigmoid. Outputs: model: the trained 1 class SVM model. YPREDA1D array containing the predicted labels for new data points. 1 indicates an anomaly. -1 indicates a normal point. Steps: training: the algorithm learns a boundary in the feature space that encloses the normal data points. Prediction: for new data points, the algorithm calculates the distance to the learned boundary. Data points outside the boundary are classified as anomalies. Metrics: accuracy: the percentage of correctly classified points normal and anomalous. Precision: the proportion of correctly identified anomalies out of all points classified as anomalies. Recall: the proportion of correctly identified anomalies out of all actual anomalies. F1 score: the harmonic mean of precision and recall. Visualization plots: decision boundary visualizes the learned boundary in the feature space, separating normal data points from anomalous ones. Scatter plot shows the distribution of data points in the feature space, with anomalies highlighted. Fine-tune parameters. Kernel: the type of kernel function used. Experiment with different kernels to find the best fit for your data. Nu: the fraction of training data points expected to be anomalies. Higher values lead to a more relaxed boundary. Gamma: the kernel coefficient. Higher values indicate more complex decision boundaries. Uncertainty methods. Confidence score: the distance of a data point from the learned boundary can be used as a measure of confidence in its classification. Higher scores indicate higher confidence. Challenges and fixes. Challenge 1: choosing the optimal kernel and parameters for the specific dataset. Sample use case: using a linear kernel for highly nonlinear data can lead to poor performance. Fixes: experiment with different kernel functions and parameter settings to find the best combination for the dataset. Use cross-validation to assess performance on unseen data. Challenge 2: handling imbalanced datasets where the number of anomalies is significantly less than the number of normal data points. Sample use case: anomaly detection in network traffic where the majority of data points are normal and anomalies are rare events. Fixes: use techniques like oversampling or undersampling to balance the dataset. Consider using outlier detection algorithms designed specifically for imbalanced data. sklearn SVM SVC. Description: the SVC support vector classifier class in scikit-learn is a powerful tool for implementing support vector machine SVM algorithms for classification tasks. SVM is a supervised learning model that aims to find the optimal hyperplane that separates different classes in a multi-dimensional feature space. Inputs: X. This is a 2D array representing the input data. Each row corresponds to a data point, and each column represents a feature. Y. This is a 1D array containing the labels or target values for each data point in X. The labels should correspond to the classes you want to classify. Outputs: self returns the trained SVC object itself, which can then be used for making predictions on new data. Decision function X returns the distance of each data point in X from the decision boundary. Steps: data preparation: the input data X and labels Y are prepared for training. Kernel selection. You choose a kernel function that defines the similarity between data points. Popular choices include linear kernel, simplest kernel, suitable for linearly separable data. Polynomial kernel allows for nonlinear boundaries. Controlled by degree parameter. Radial basis function RBF kernel widely used. Creates nonlinear boundaries with a Gaussian-like influence. Hyperparameter optimization. Parameters like C regularization strength, gamma kernel coefficient, and others are tuned to achieve optimal performance. Model training. The SVC algorithm finds the optimal hyperplane by maximizing the margin between the classes. Prediction. The trained model can be used to predict the class labels for new data points. Metrics. Accuracy. The proportion of correctly classified instances. Precision. The ratio of true positive predictions to the total number of positive predictions. Recall. The ratio of true positive predictions to the total number of actual positive instances. F1 score. A harmonic mean of precision and recall. Balancing both metrics. AUC area under the curve measures the overall performance of the model, particularly when dealing with imbalanced datasets. Visualization plots. Decision boundary plot visualizes the separating hyperplane in 2D or 3D space, showing the decision regions for different classes. Scatter plot with support vectors displays the input data points with support vectors highlighted, indicating the data points that contribute most to the model. Fine-tune parameters. C regularization parameter. Higher values emphasize correct classification of training data, potentially leading to overfitting. Lower values allow for some misclassifications, which can help with generalization. Kernel. The kernel function to use. Different kernels. Linear, polynomial, RBF are suitable for different types of data. Gamma kernel coefficient for RBF and polynomial kernels controls the influence of individual data points. Higher values give more influence to nearby points, while lower values consider a wider range of points. Degree of the polynomial kernel. Higher degrees create more complex decision boundaries. Uncertainty methods. Confidence scores. The decision function output provides an indication of the model's confidence in its predictions. Higher values indicate greater confidence. Challenges and fixes. Challenge 1. Overfitting. When the model performs very well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1. A high value of the C parameter, combined with a complex kernel, might lead to overfitting. Fixes to challenge 1. Reduce the value of C to allow for some misclassifications. Simplify the kernel or choose a more suitable one, e.g., a linear kernel if the data is linearly separable. Use techniques like cross-validation to tune hyperparameters and evaluate model performance on unseen data. Challenge 2. Computational complexity. Training SVC can be computationally expensive, especially with large datasets and complex kernels. Sample use case that resulted in challenge 2. A dataset with millions of data points and an RBF kernel might lead to long training times. Fixes to challenge 2. Consider using a simpler kernel like the linear kernel if appropriate. Use techniques like dimensionality reduction (PCA) to reduce the number of features. Utilize parallel processing or GPUs to accelerate the training process. Challenge 3. Data scaling. Scaling the features to a common range, e.g., 0 to 1 can improve the performance of SVM. Sample use case that resulted in challenge 3. Features with widely varying scales can influence the model's performance. Fixes to challenge 3. Use standardization or min-max scaling to bring all features to a similar range. Consider using specialized techniques like robust scaler if the data has outliers. Challenge 4. Choosing the right kernel. Selecting the appropriate kernel function is crucial for effective classification. Sample use case that resulted in challenge 4. An RBF kernel may be unnecessarily complex for linearly separable data. Fixes to challenge 4. Start with a simpler kernel, e.g., linear, and gradually increase complexity if needed. Use cross-validation to evaluate different kernels and choose the one that performs best on unseen data. sklearn SVM SVR. Description: the support vector regression SVR model in scikit-learn. sklearn is a powerful technique for regression tasks, aiming to find the best fit line or hyperplane that minimizes the errors between predicted and actual values while considering a margin of tolerance epsilon. It utilizes the concept of support vectors, which are the data points closest to the decision boundary, to define the model. Inputs: X. The input features, typically a 2D array with each row representing a sample and each column representing a feature. Y. The target values, a 1D array corresponding to the output values for each sample in X. Outputs: model. A fitted SVR model, containing the learned parameters. Predictions: the predicted values for new input data, generated by the trained model. Steps: data preparation. The input data X is pre-processed, which may involve scaling, normalization, or feature engineering to improve model performance. Model initialization. An SVR model is instantiated with specified parameters, such as the kernel function, regularization parameter C, epsilon, and others. Model training. The SVR model is trained using the provided input features X and target values Y. This involves finding the optimal hyperplane and support vectors. Prediction: the trained SVR model is used to make predictions on new data. The model calculates the distance of new input points from the decision boundary and estimates the corresponding output values. Metrics: mean squared error. MSE measures the average squared difference between predicted and actual values. Root mean squared error. RMSE the square root of MSE, providing a more interpretable measure of error in the same units as the target variable. R squared. R2 represents the proportion of variance in the target variable explained by the model. Higher values indicate a better fit. Mean absolute error may measures the average absolute difference between predicted and actual values. Visualization plots. Scatter plot visualizes the relationship between the input features and target values, with the predicted values overlaid for comparison. Residual plot shows the difference between predicted and actual values, helping to assess model bias and identify potential outliers. Learning curve plots the model's performance on training and validation sets as a function of training data size, helping to identify overfitting or underfitting. Fine-tune parameters. Kernel defines the function used to map data to a higher dimensional space. Common options include linear, RBF, poly, and sigmoid. See regularization parameter that controls the trade-off between fitting the training data and preventing overfitting. Higher values prioritize fitting the data, while lower values encourage smoother models. Epsilon tolerance margin around the decision boundary. Data points within the epsilon margin are considered correctly predicted, regardless of the actual distance. Gamma specifies the influence of a single training example. Higher values indicate a larger influence, potentially leading to overfitting. Uncertainty methods. Confidence intervals provide a range of likely values for predictions, based on the model's uncertainty. Challenges and fixes. Challenge 1: Overfitting. Sample use case that resulted in challenge 1 using a complex kernel function or a large C value can lead to overfitting, resulting in poor generalization performance on unseen data. Fixes to challenge 1: Use a simpler kernel function, e.g., linear, reduce the C value, or consider techniques like cross-validation to prevent overfitting. Challenge 2: Underfitting. Sample use case that resulted in challenge 2 using a linear kernel or a very low C value might result in underfitting, where the model fails to capture the underlying patterns in the data. Fixes to challenge 2: Try a nonlinear kernel function, increase the C value, or consider adding more features to the dataset. Challenge 3: Scaling of features. Sample use case that resulted in challenge 3 when features have different scales. The model might be biased towards features with larger ranges. Fixes to challenge 3: Scale the features using techniques like standardization or normalization before training the model. Challenge 4: Choice of kernel function. Sample use case that resulted in challenge 4: Selecting an inappropriate kernel function can lead to poor performance. Fixes to challenge 4: Experiment with different kernel functions and choose the one that performs best on the validation set. Challenge 5: Handling outliers. Sample use case that resulted in challenge 5: Outliers can significantly affect the model's performance by pulling the decision boundary towards them. Fixes to challenge 5: Pre-process the data to remove or handle outliers, or consider robust regression techniques that are less sensitive to outliers. sklearn SVML1 Description. This function computes the minimum C value for which the solution of the linear SVM problem is non-empty. It is useful for choosing a suitable value for the regularization parameter C in linear SVM. Inputs. X the training data, where each row represents a data point and each column represents a feature. Y the target labels for the training data. Outputs. L1 the minimum value of C for which the solution of the linear SVM problem is non-empty. Steps. Compute the dual coefficients for the SVM problem with a given C value. Check if the dual coefficients are all non-zero. If all dual coefficients are non-zero, then the solution is non-empty. If not all dual coefficients are non-zero, then the solution is empty. Increase the C value and repeat steps 1 to 4 until the solution is non-empty. The minimum C value for which the solution is non-empty is the L1 Metrics. None. Visualization plots. None. Fine-tune parameters. None. Uncertainty methods. None. Challenges and fixes. Challenge 1: The function may return a very small value of L1 which may result in overfitting. Sample use case that resulted in challenge 1: The training data is very noisy or has a high number of features compared to the number of data points. Fixes to challenge 1: Try increasing the value of C manually or using a grid search to find a suitable value. Challenge 2: The function may take a long time to compute if the data is large. Sample use case that resulted in challenge 2: The training data has a large number of data points or a high number of features. Fixes to challenge 2: Try using a smaller subset of the data or reducing the number of features.